Hello and welcome to the image processing and image analysis session of the GeoDict user meeting. My name is Andreas Griesser and I will give a talk about artificial intelligence for image processing in GeoDict 2023. First of all, let me introduce myself. I am business manager for image processing and image analysis at Math2Market, and I've been with Math2Market since 2014. I did my master's degree in computer science in 2016 and have been with Math2Market full-time, first as a software developer and now also as a business manager since 2016. Now, to get to the actual topic of the talk, let's have a look at this overview slide. You can see a brief summary of all the steps we consider part of the image processing and analysis workflow in GeoDict. Here the workflow is split up in 4 steps. First of all, importing and handling data, so for example, cropping the images or aligning them. Second, filtering and enhancing the images to get rid of artifacts and noise. Third, the segmentation of the image. And finally, fourth, the analysis of the image to get geometrical properties of your material. Each of the first 3 steps is essential in obtaining correct and meaningful analysis and further down the road in even simulation results. In the past years, AI and especially deep learning methods have driven many innovations and breakthrough results. For this reason, we keep pushing forward what we do with AI in GeoDict. With GeoDict 2023, we apply AI-based methods for image enhancement in the filtering step, image segmentation, and for image analysis in FIB-SEM and GrainFind. First of all, I will talk a bit about the improvements we did to the AI segmentation in import GeoVol compared to previous GeoDict versions. Then I will go on and highlight what we can now do with AI-based image enhancement with the help of GeoDict AI and showcase a few examples here. And finally, I will talk about the improvements we did to the FIB-SEM and FiberGeo workflow to get your FIB-SEM results more easily into FiberGeo. Let's have a look at the AI segmentation. We introduced the AI segmentation in GeoDict 2021. Since then, it has helped in many applications where classical image segmentation methods struggle, such as, for example, FIB-SEM images. We received a lot of positive feedback and suggestions on what could be improved to make it even more helpful. The first few improvements we incorporated in GeoDict 2023 are displayed here. We reordered the user interface a bit to better reflect the workflow you are actually doing when using the AI segmentation, and we reduced the memory consumption of the boosted tree and newly added random forest method by roughly 50%. And of course, with the addition of more than 16 materials to GeoDict, we also added support for this in the AI segmentation. But what might be one of the highlights for the everyday use of this method is the new mixed mode preview. In previous GeoDict versions, you could set the overlay to either display the labels and add new labels or the current preview of what your model would segment. So that is the switch you can see here in the user interface. And now with the new version, you can set that switch to a mixed mode preview, where you see the labels and the preview of your model at the same time, as it is displayed here on the right side. You can see here there is a label in a bit more opaque, and everywhere in the image there's the preview. And in this mode you can also add new labels, which makes it easy to start with a few labels, compute the preview of what your model would segment, and then add new labels in the areas where errors are obviously visible. Another new addition to the AI segmentation is the random forest method. Similar to The random forest method works similar to the boosted tree method, and it computes some feature images and then uses a decision tree based model to learn and later on predict the segmentation. But it works a bit differently. It's generally considered to be more robust against noise in your input data, but there might be cases where one or the other is better. The random forest method is very widely known and commonly used, so we added it to GeoDict. Another addition to these decision tree based models was that you now can select which feature images you want to compute for your AI model. So in previous versions, these feature images, such for example as a Gauss filtered image, were always the same. They were hard-coded in the method, but now you have that select features button. You can see on the top right here. And if you click it, you get this window where you can configure all the features that should be computed. And you can see on the right bottom, there is this gray value image with the two computed previews on top. On the left side, we have the features configured to compute 3 Gauss images, one with a sigma of 1, one with a sigma of 5, and one with a sigma of 10. And the neighbor voxels of each voxels in a distance of 1, 2, and 3 voxels are used too. Compared to this, on the right side, we only use one Gauss image with a sigma of 1 and only the direct neighbors of a voxel. And as you can see, the segmentation on the left, while still not perfect, is a lot less prone to the streaks that we see on the right side. Of course, the computation time of the method on the left side is a bit higher and it also requires a bit more memory, but you can now configure this and make a trade-off as if required. Of course, beside the decision tree-based methods, there are still the unit-based methods, and these are the methods for the really complex cases where you need that powerful deep learning AI to segment your image. And we also did improvements to that. So first of all, we enabled the strides training mode we added last year to GeoDict by default now. This makes the training roughly 10 times faster than the old training mode, and the results are also better for most realistic cases. And on top of that, we optimized the application of the UNet 3D, and that is now also 10 times faster than it was in GeoDict 2021 and 2022. This improvement is included in Service Pack 1 of GeoDict 2023, which should be released by now. And if you want to test out all these improvements to our segmentation and the speed ups of the unit segmentation, you can do this on the example datasets you can see here on the right side that are now included in your GeoDict installation if you check the box in the installer. The next thing I want to talk about is the image enhancement in GeoDict AI. With this new method, you can train an AI model on a pair of CT scans, a low quality and a high quality scan of the same sample. And the AI model will learn to transform a CT scan from the low quality image to the high quality image. The workflow is shown here. We start on the left side with the image acquisition, where you take, as I mentioned, a low quality and a high quality scan of the same samples. In this study, we used short and longer exposure times. We then take these pairs of scans to GeoDict AI and train the model. And afterwards, we can apply this model to the low quality CT scan to obtain a high quality CT scan, but without all the time needed in the CT scanner. And of course, we cannot only do this with samples that were in the training data set, but we can do then, if we want to do a lot of scans of similar samples, for example in a core lab, apply the AI that we trained on the first few pairs of samples to all the other samples that we will have in our series of samples, and save a lot of time in our CT lab. The image acquisitions for the samples I will be showing here were performed by Viswasanti Chandra at KAUST University. They acquired pairs of high and low quality samples of heterogeneous carbonate samples. They were scanned at a resolution of 30 micrometer on a TESSCAN Core-TOM micro-CT. The sample size was 1 inch and the resulting dimensions were roughly 1000 cubic voxels. On this slide, you can see the 4 reservoir carbonate rock samples that were scanned for this study. Of course, these are only the high quality images. They are all from the same rock formation. They have the same diameter. So the plugs have the same diameter. They were scanned at the same resolution. And the difference between the low quality and the high quality samples in this case was that the exposure time of the low quality samples was a lot lower, which resulted in worse contrast and a lot more noise in the image. But of course also the scan time was about 80% faster than it was for the high quality images, which of course would increase the throughput of your CT by a lot if you were able to apply this method in your production environment. Here you can see the results of our first feasibility study. The leftmost image is the low quality scan with the short exposure time. You can see it has a lot of noise and there is way less contrast than on the right and on the image on the right to it, which is the high quality image with the long exposure time. So there's a significant difference between these samples. And we trained our AI on these 2 cases and afterwards applied it. And you can see the results to the right. So the third image, first of all, is the low quality image, but just with a non-local means filter applied to see how that would perform compared to our method. And on the rightmost image, you can then see the result of applying the AI that was trained on the first 2 images to the low quality image. Of course, in this case, our training data and the data we apply is the same because this was just the first feasibility study. You can see the contrast of the image that was processed with GeoDict AI is a lot higher than just the non-local means filtered image, and also the noise is basically completely gone. The quality is comparable to that of the high quality scan. It might be a bit more blurry in some places, but it's definitely a lot better than the low quality scan or the non-local means filtered version of the low quality scan. Of course, only using the data you've trained your AI model for the application of your AI model is a bit of cheating. So we also had a study where we did not train the AI on the same model we applied it on. So this can be seen here. We have on the left side the low quality scan, in the middle the high quality scan, and on the right side the result of the GeoDict AI model that was not trained on this sample. And as you can see again, the noise is a lot less than it was in the original image. And the contrast, especially in the pores on the right bottom side of the scan, you can see is a lot better. And the noise and the contrast together make it a lot easier to segment this image. So this is a really, really promising result. And we will continue to investigate what we can do with this method to improve your images and save you time with your CT scanner. To summarize everything, with GeoDict AI, we can now enhance gray value images. and enable a reduction of your CT scan time in your lab by approximately 80%. And by this means increase the throughput of your CT machines significantly. In the future, we will also investigate how we can apply this method and how well it works for upscaling CT scans from lower resolution to higher resolution. Last but not least, I want to talk a bit about FIB-Geo and FIB-Find and how to create a digital twin with FIB-Find. So starting from your micro CT scan, we segment that and we can put that into FIB-Geo, and we can obtain basically every geometrical parameter you can come up with. For example, the fiber diameter distribution, the orientation of the fibers, the curvature of the fibers, and so on. With these parameters, we can then, to create our digital twin, go into FIB-Geo and enter most of them directly. We cannot enter all of them yet directly. For example, the curvature is described differently, and we have to use a bit of experience to get similar curvature parameters to what the original CT scan has. After we generated the model with FIB-Geo, then with GeoDict 2022, we still need to run FIB-Find AI again on this CT scan, on our generated model, to obtain the same parameters we had for our original structure. And we can then compare them to make sure we have an actual digital twin on that, not something completely different, which would be not good. So if some of the parameters do not fit yet, then we have to go back into FIB-Geo and change our parameters around, run FIB-Find AI again to get again the results that we can compare to our original structure. So that's of course a bit annoying that we have to rerun FIB-Find AI every time, even though the individual fibers are already in the FIB-Geo result. So with GeoDict 2023, we changed this. With the new version, we directly incorporated the geometrical statistics you get out of FIB-Find into the FIB-Geo result, because the individual fiber information is already contained in the FIB-Geo model. So you can now, without rerunning FIB-Find AI for every iteration of your model, directly compare the results that are contained in the FIB-Geo result now with the results you get from the FIB-Find AI output of your original structure. This will make the workflow of creating a digital twin based on the geometrical properties a lot easier and faster. This is the conclusion of my talk, and I want to thank everybody for their attention, and I hope I sparked some interest into you to try out our new version.